I've got the steps for finding an arc length parameterization with a given reference point up here on the board. So to find R of S, which would be the arc length parameterization with reference point T naught, and I guess I could also add to that preserving the orientation. So I start with an oriented curve, and I'm going to keep that same orientation. Whatever was the positive orientation for T is going to be the positive orientation with respect to S. Okay. First thing I do is I find the arc length function. That's just integrating from my reference T value to T, the magnitude of the derivative. Okay. Now, if my curve is smooth, and in some cases even if the curve isn't smooth, but guaranteed to happen if it is smooth, that will be a one-to-one function, and then we will be able to reverse that and solve for T in terms of S. Okay. Once you have that, that gives you a way of describing T in terms of your new parameter S. You plug that into the original parameterization. So you started with an R of T. What you're plugging in then is a way of describing T in terms of S, and so you're essentially getting a formula in terms of S, and that's your arc length parameterization. And then it's very easy to forget this last step. Solve for your restrictions on S. If there were restrictions on T, that's going to induce some restrictions on S. So if we had a situation where T had to be between A and B, then S is going to be between the two corresponding arc lengths, the arc length at A and the arc length at B. In our last example, we just had that T was bigger than or equal to 0, so we got that S had to be bigger than or equal to the arc length at 0. And since 0 was our reference point, it was just bigger than or equal to 0. Okay. Now, when people get to this step, I often see students do way more work than they need to do. Notice, I can figure out what the arc length is at A and B by plugging into the result from step 1. Okay. So I often will see people find the T and say, oh, I've got the T values. They'll use the fact that they've solved for T in terms of S, and then they'll redo all of that work to solve back for S. Just use the formula from step 1. Okay, excellent. Now, it is possible for there to be no restrictions on T, but still there are some restrictions on S, because it's entirely possible to have an infinite T interval that maps to a curve with finite arc length. Okay, I'm not going to ask you to do step 4 unless I either explicitly tell you to, or there were restrictions on T. So if you've got a curve where an infinite T interval maps to a finite arc length, so that there were no restrictions on T, but there are now some restrictions on S, I'm not going to expect you to figure that out on your own. If that happens, I would tell you, and I would say solve for the restrictions on S. But otherwise, if there are restrictions on T, you know there will be restrictions on S, and part of finding the arc length parameterization is finding those restrictions. It's really easy to forget that, especially because this can be a very long and time-consuming process. So it's easy to skip that, and it's kind of frustrating because you've spent so much time with the harder parts, and this is usually pretty straightforward because all you're really doing is plugging A and B into the formula that you already found in step 1. Okay, so let's just try another example. I want to take a look at an arc length parameterization for a circle of radius A. Okay. So let's just suppose I have R of T is equal to A cosine T, A sine T. Okay. And A is going to be my radius, and by saying that it's the radius, I'm saying that it's a positive number. Okay. Okay, so here I've given you a circle of radius A. It's oriented counterclockwise. Now, if I don't restrict the domain, then I would just be drawing that circle again and again and again and again and again, and that's totally fine. The way we would interpret that arc length is, let's just say our reference point, reference time, is 0. Okay. So that would be starting at this point right here. Okay. Well, the arc length that I would get at time 2 pi would just be the circumference of the circle. If I've got t values past 2 pi, so I've started to draw the circle a second time, we're just going to accumulate more arc length. So at 4 pi, I would have traced the circle twice. My arc length would be twice the circumference of the circle. Okay, excellent. So let's see if we can't find our arc length parametrization. So I'm going to just write this in terms of my dummy variable. So r of u is a cosine u, a sine u. Then r prime of u is going to become negative a sine u, a cosine u. So the magnitude of r prime of u is going to be the square root of a squared sine squared u plus a squared cosine squared u. That's the square root of a squared times sine squared u plus cosine squared u. Now, of course, this is just 1, so that's just the square root of a squared, which would be the absolute value of a. And since a is bigger than 0, because we defined it to be the radius of our circle, that's just a. That's actually kind of nice. That tells us this standard parametrization for a circle is one that's always drawn at a constant speed, where that constant speed is just the radius of the circle. Okay. So for the unit circle, the standard parametrization that we have of just cosine t sine t, that already is an arc length parametrization. We're drawing that at a constant speed of 1, so that every time our parameter increases by 1, we've drawn 1 more unit of curve. Okay, excellent. So that's going to make finding my arc length function pretty nice, because I've got a very nice integrand. So now I can say s of t is the integral from 0 to t of a dt. Sorry, oh, horrible, du. We must have a dummy variable. We cannot have the same thing here and there. Bad teacher, bad teacher. Okay, so when I have this, I'm just integrating a constant. I know I'm going to get that constant times the length of my interval. And the length of my interval is just t minus 0. Okay. I could certainly do that algebraically. I'm actually thinking of this more geometrically. I'm getting the area of this rectangle, constant height of a, length of the base is just t. Now I've drawn it here with t being positive. If t happens to be negative, I'd still be getting this. It's just my base would now be a negative number. Okay, excellent. So now we've got s is equal to a times t. Very easy to see that that is a one-to-one function. I can very easily solve for t. T is just going to be s over a. Not a problem to have a in the denominator because we said it was our radius and it was positive. Okay. So then, to get my arc length parametrization, that would just become r of s is equal to, I'm going to replace t with s over a. So it would be a cosine s over a sine s over a. Okay. So that function composition changes the speed with which we're drawing the curve so that we're drawing things at a constant rate of 1. And again, that's going to make it easier to study certain purely geometric properties of the curve where I'm not thinking in terms of an application where my parameter is time and actually has a meaning in the context of the problem. The arc length parametrization allows me to really just focus on the curve and its geometric properties.